C that E values right here. Okay, just check yourself really fast. I'm looking for completion. Okay, I'll do it. It looks like I'm on the Thank you. Okay, Clayton. You're a good person at heart, no matter what Maggie says about you. All right, so I'm apparently gonna do number 4, okay? So number 1 through 3, you're good? Okay. Before I move on, before I actually do number 4, which of these is the best battery? 2. Why?
The highest cell value.
Okay, so it creates the most volts. So is that, you guys know what's a normal battery's voltage?
1.
Okay, there are 12-volt batteries. That's like what, a long battery? 9 volt, what's lower than that?
6 volts.
Okay, a AA is like a 1.5 volt battery. So that's better than a 1.5 volt battery. Woo! All right, so we can make better batteries with chemistry. Actually, all batteries are made with chemistry, guys. Number 4 said was it iodate and periodate? Iodate and periodate. Yeah. And manganese and permanganate. So, metal salt bridge. There's my electrodes. Oh, it's a little ugly here. We got it. We had, which was the higher reduction potential? Which was the higher E value? Periodate or iodate? Iodate. The iodate combo or the manganese combo? So this one was 1.539 volts, and what was the other one? So that's that one. That's a V, by the way. What was the manganese one? 1.51 volts. Okay, so which is the anode, without looking at my stuff, okay? Which is the anode? Because why? Right, so I told you guys yesterday to note that the lower voltage for so if you're setting up a galvanic cell, E must be positive, and that's why all of these are positive, okay? So galvanics have a positive E cells, so that's the anode and that's the cathode, because when I do my subtraction, I do cathode minus anode, or reduction minus oxidation, and that's going to yield a positive value. So that's the permanganate one. It's going to be over here in the anode, and I'm putting the anode chamber over here, the cathode chamber over here. Anode is going to be Mn2 plus and permanganate, and the cathode is the iodate and the periodate. And I'm just choosing carbon here for graphite, or platinum, it doesn't matter. I'm just choosing the cheaper version. And then what else do we need to note here? The voltage flow is going from the anode chamber to the cathode chamber, so the electron flow is from left to right. And then I'm actually going to write out the BCE over there. Okay, so E red minus E ox is E cell. So that would be 1.539 volts minus 1.51 volts to give us a 0.03029. volt difference. It's still positive, but it's a really low voltage, so it's a really crappy battery. Okay, there's not a large reduction potential difference between them, so there's not a strong pull for electrons from left to right. In the salt bridge, you have to denote which is the ion that flows towards the anode, which flows towards the cathode. What ion or what charge ion would go towards the anode here? Y minus. That's a cheap way of saying it. And you say a more expensive way, more educated way. So this anode is losing electrons, right? Because it's undergoing oxidation. What is its charge after it loses? Okay, so it contains kind of that inherent, kind of a positive charge over the whole entire anode. So to neutralize that, to limit charge buildup, you must send an anion towards it. Okay, to neutralize that charge buildup. This side, as it gains electrons, because it's undergoing reduction, it's going to take on a negative charge, and as it takes on a negative charge, we have to neutralize that charge buildup by sending the cation towards it. Okay, so you need to, don't just memorize it, you have to explain it. Okay. The external wire is the electron flow, and then the balancing part of this, you guys had a balancing acid. So you had iodate was the one that was reduced. Yes, iodate was the one that was reduced. Yeah, so you're the cathode. So iodate yielding periodate. What do I need to do to balance? Actually, I lied. This is an oxidation state of, what's the iodine's oxidation state here? So +5, so that's a -2 times 3 is a -6, so that's a +5, and this is a +7, so that looks like it's being oxidized. I need to flip this because I need to have it reduced, so it's the periodate going to iodate. So it does take some manipulation at first, and then what do I need to do now? Okay, so I add 1 water here, that satisfies my oxygens. I add whatever here, 2 H pluses, and this overall charge is what? Yeah, so 2 plus and a -1 is a +1 overall, and this is a -1 overall. So what do I need to add on this side? 2 electrons. And then that's it for the iodate one, and the permanganate was, if this one's being reduced, the permanganate's being oxidized. So Mn should go to MnO4. Yeah. And, oh, remind me, I'll show you the PowerPoint for teal today, because I looked up some stuff after you guys asked me questions yesterday. Okay, so those are manganese going to permanganate. What do I do? Okay, so 4 waters over here to satisfy, oops, that's a random one up there, okay. To satisfy my oxygens here, and then 8 hydrogens on this side, or H pluses on this side. Overall charge over here. So permanganate and an 8 plus H plus is going to give us 7 plus here. We have a 2 plus here. What do I need to do? So 5 electrons. You'll see this kind of reversed than what we normally do with permanganate. Then you have to multiply by 5 and 2, equally on both, or opposites on both for half reactions here. And your overall VCE would be 5 iodates. I'm sorry, periodates, plus 2 manganese, 2 pluses, plus 3 waters after you simplify your waters out, yields 5 iodates, 2 permanganates, and 6 H pluses. It's like I have a recipe for something crazy here. So that one's a really complex one. You'll see there's no solids whatsoever, so we had each platinum or graphite in this one. Okay? And then the cell diagram was, the cell notation is when we have it across with all the lines. The cell diagram is like this. The diagram, cell notation. Cell notation was with your platinum or graphite. Anode was manganese and permanganate. Salt bridge, iodate, and periodate, platinum. Okie dokie? I think that's everything you had to denote there. Yeah. All right. Yeah. That's it. There's no like difference in the voltage gradient. We just need a solid metal electrode that's conductive. Graphite's really conductive, and all metals are very conductive. Yeah. So you have to select. So if you don't have, for example, in our examples up here, This first one is aqueous and gaseous, no solids. And the electrode itself is what you connect the alligator clips to for a battery to measure its voltage. And a wire has to be connected to something solid. You have to put a solid there. And that's when I use platinum or graphite, anything that has 0 solids in their actual reaction. So this one is good because there's a solid here and here. So that one didn't require platinum. This one required platinum or graphite. This one required platinum or graphite, and this one did too. Okay. All right. There's 2 more things I didn't tell you yesterday, and then we're just going to talk about cell potential briefly, maybe 15 minutes, and then we're going to work online on some simulation stuff. Okay. And then tomorrow we have a lab called microvoltaics. If you guys want to find that in your pocket, make sure you know what it is. It's a Logger Pro lab, so it's kind of it looks like the Logger Pro labs. Yeah. Yeah. I know. I'm gonna go. I'm trying to get teachers to go with me.
Like Michael Coker, Master Holland.
I know. I've had half the. I had to get the list to make sure it was like. I said it to myself. If ever half people I've taught, and I'm going. So I'm going.
Friday, since we're going early because there's a dive. We have one diver and he's diving on Friday, so we'll leave like
Who's the diver? Who's the diver?
Patrick O'Brien. He's about he's super good. He's a freshman. He always almost wins.
That's awesome. I sent out an email to the entire staff. I was like, does anybody want to carpool to Greensboro? Going to support swim team. And Miss Whitley emailed me back. She's like, I have an event, but I'm going to make signs. She's going to make me signs right now. Okay, so back to chemistry. Here, this is the one part I didn't talk about yesterday. With me? Okay, this is the one part I did not talk about yesterday, and it's the part about the external wire. Why in the heck are we putting an external wire on this device? Yeah. Right, and so, but why? I mean, aren't the electrons going to transfer anyway? Well, if I put a beaker of copper in silver nitrate, for example, an electrode, so like a piece of solid copper, and I put it in silver nitrate, isn't it going to do its little redox thing in here? Right, the copper is going to change to, or actually, this would go to, I want to collect silver. Yeah, the silver would plate on the copper, and the copper would go to copper 2+. So the exchange of electrons would occur. But can I capture those electrons? No, they're just doing their thing. They're exchanging it surface on surface. So I can't do anything. I can't capture the electrons. I can't siphon them off. I can't use them for electrical energy. So I have to find a way to separate the redox reaction into chamber and chamber, and then put a device in between or some sort of way to siphon off the device or the electrons, and that's me, abusing chemistry and taking the electrons away from the redox reaction. But I, supply back those anions and cations to limit the charge buildup. So we have to have an external transfer device to capture the electrons. And the whole do work part, do you guys remember work? Work is equal to. Okay, I know Q is equal to MCAT. Okay, I hear that. Work is equal to.
Wait, hold on. No one's saying it. I wrote this down and that's mine.
You're right. Okay, it's a negative P delta V, but there's more. Work is coming into play with delta G. You wrote this down in your outline. Nobody but Maggie.
I just have that it equals negative work equals potential.
Okay.
Potential self.
Okay, so that's related. So work is equal to cell potential in some way or form. Okay, so we're going to get into the actual equation with work tomorrow, but work is just a way that we talk about free energy. Okay, so work and Gibbs free energy are directly related to each other. So the whole electron flow can do work means it's going to be related to Gibbs free energy, which means I can relate this to thermodynamics and all kinds of other things. Okay, this was the FRQ. I'm not going to do this FRQ. Yeah, that's actually a charge. We'll get into that, yeah. It is related to E cell and coulombs, which is a unit of charge. So I'm going to show you this frightening FRQ that everybody was a little scared of when we first saw it last year. A metal air cell. First off, okay, so a metal air cell, a new type of portable energy source consisting of a metal anode and an alkaline electrolyte paste, so a basic paste, contains water, porous cathode membrane, allow the oxygen from the air in. The schematic of the cell is shown above. Reduction potentials for the cathode and 3 possible anodes are given in the table below. So this is how they would give you the cell potential differences in a small table, not a huge, humongous list like I gave you guys yesterday. They show you the electron flow, and they show you oxygens here, and they say unknown metals here, right? Then they give you a little bit more information, and it says this is the reaction, and it says calculate the cell potential. If you had to figure out the cell potential of this, you could do this. At first, you're like, an aerosol, what the heck is that? It just means that there's some sort of gas that's available to be used. Using this information and the fact that it says voltmeter up here, you're probably seeing that this is what kind of cell? Galvanic cell. You're seeing the galvanic cell here because an electrolytic cell requires you to force energy in, so it would say DC up there, meaning direct current. We're going to get into that later. But the voltmeter is saying it's galvanic, so the E cell must be what? Positive or negative, right? Positive. So looking at this list, which are the two things that are of interest to us? Which two reactions? Okay, so I hear the first one because we have oxygen here because this is an air cell, and the zinc, right? Which is the cathode? Which is the cathode? How do we make E cell? Right, E cell is E red, which is cathode, minus E ox, which is the anode. So the cathode for this one is cathode is oxygen, and the anode is what's up? Wait, continues to slay. Okay. So these values here, you would take 0.34 minus a minus 1.34. So what would this cell voltage be? Positive 1.65. Okay. So you can do that in your head. You can do it without actually learning the rest of electrochemistry. Draw an arrow for the indicate the direction of the migration of the hydroxide ions. You could continue to do that. Here, driver Katie, just leave them right there. Thanks, Logan. So I just want to show you that you know how to do parts of these FRQs already. We'll kind of work through the rest of them. Okay, so I'm going to skip the video for a second. This is on your packet. Some of it's in your packet. It's going to say notes. It's probably the second, like page 2. Page 2, subsequent to electronics. Okay. We have talked a little bit about this. I'm just going to highlight the last couple of details because these are really good multiple choice questions that you will get wrong. How don't you get them wrong? Okay. So anytime you write down a reduction potential, it is the reaction being reduced, right? You're like, duh, it says reduction potential. None of these reduction potentials on your list are written oxidized. None of them. So that's why some of you guys yesterday are like, which reaction is it? I have one on my paper that's flipped because your reactions, half reactions you're writing, they were oxidized. But look on your list of reduction potentials like this. You notice where are the electrons on this list? Reactants or products? Your list that you have a large list. The electrons are all in the what? They're all in the reactants. So each of these half reactions are written as a reduction reaction or reduction half reaction. So that's why I'm telling you that when we're doing our subtraction, we're doing the one that is reduced minus the one that is oxidized, because that minus there serves for us flipping the sign that you read about in your study guide reading, or reading guide reading, because when we're subtracting, we're actually talking about the opposite nature of the reaction. We're talking about the anode, we're talking about the oxidized one, but when we subtract, we're actually satisfying that need. So that's why I'm always going to use that one, just because that's what I learned it a million years ago, and that's why I stick with, so I can stick with one. You'll see a different versions of that. So how do we figure out these reduction potentials? On your list, do you see the She, which is the standard reduction potential for hydrogen? It says, find it. It says 0.00. 2 hydrogens plus 2 electrons. 2 hydrogen ions plus 2 electrons yields hydrogen gas. And it says 0.00. Okay, so you see that's called the She. It's the standard hydrogen electrode, and that's what we compare everything to. So everything that is more positive than the standard hydrogen or the She, everything that's more positive is more likely than hydrogen to be reduced. Yeah. Yes, this one is 0.00 volts. So everything on everything more positive than hydrogen's, the standard hydrogen electrode would be more likely to be reduced, and everything that's less than that would be, or meaning negative, would be more likely to be oxidized. So looking on your list, you've got 2 lists there. What are some common things that have positive electron or positive voltages, positive cell potentials? Look at your list in your paper. Things like what? Some halogens. So at the very top, your halogens are very likely to be reduced. What else? Some of your oxidizing agents, right? And then some weird metals like mercury and silver. Okay? And then what are some things that are negative being, likely to be oxidized? Okay, water, what else? Water is actually easy to go either way. Alkali metals, alkaline earth metals, some active metals. Again, what does the term active mean? You need to know active metals means what? Likely to give off electrons, meaning
Oil.
redox is a umbrella term. It's going to be oil, right? So active means likely to oxidize itself, right? Give off electrons itself, which means likely to reduce something else. So you're kind of right saying it's doing both, but itself is being oxidized, so it's giving off electrons. Okay, so we're going to look at the total activity series and the reduction potential list in just a second. Whenever we're talking about E cell has a name. It's called electromotive force, or EMF, and we can refer to it in many ways. I usually just say E cell, but I want you to be comfortable calling it the electromotive force, or EMF, as well. And it's just talking about the force of electrons, or the flow of electrons, the likelihood of electrons flowing from anode to cathode. So just like in a on a hill with water, you can have a shallow hill, so a potential energy for water flowing here to here. Okay, so that's a pretty gradual slope, not a huge potential difference, right? Not a huge potential difference. What would be a huge potential difference for like water flowing downhill? Something very steep, like this, right? What did you say? Summit plummet. Okay. So we have this is supposed to be indicative of the difference in cell potentials, just like water flowing downhill. If there's a large potential difference, it's going to flow very fast, where this one's just kind of meander down. So that's the same story with cell potential differences. Okay, so the larger the difference between the two electrodes, the better the battery, because there's more force in the electrons. Thumbs up when you get here. Okay. I just have a couple more things to here. How much more, though? I was going to do them yesterday, but we got off on a Breaking Bad tangent, which, if you've not seen, you need to watch. Encourage you. I'm not, but it's just educating yourself. Educating yourself.
Educating yourself.
Okay. So, on other cultures. Okay. Other cultures. So, whenever we look at, this is the one that's in your book, you have a very similar version to this. We're seeing all of these written as reduction potentials. If on a multiple choice question it says, what is the oxidation potential? I will never myself ask you for an oxidation potential because I don't like you to mix up your science too much. If they ask you like on a multiple choice on the AP exam, what you do is it's just the opposite of the reduction potential for that given half reaction. So if I asked you for the reduction potential for chlorine gas, that's the reduction potential for chlorine gas, positive 2.866. The oxidation potential is just a negative 0.2866. So just look inside, but I will usually never ask for that because I don't want you to mix up your signs. So everything up here is really going to be, itself is reducive, meaning a good oxidizing agent, and everything down here is going to be easily oxidized, meaning a good reducing agent. So remember you flip your terms with that. Anything you need to add to this? Anything new yet? Can I go forward? Okay. This is yours. I just want to show you this is the one in your book. It's pretty. Okay. Oh, and this was just a cartoon. I'll show you. Oh, no, I do want to show you this one. What you'll realize is there are some similarities between the activity series that we kind of have somewhat memorized, meaning group 1A, group 2A, first row transition metals, second row transition metals, copper is unusually low. The activity series at the very top are the ones that are going to do what? Oxidize, and on the reduction potential list, we're the ones that are going to oxidize. It's in order at the very bottom. So there are some comparisons we can make between them. These are likely to lose electrons, meaning they're likely to be oxidized. Okay, these are the things that affect E cell, or the cell potential difference, or electromotive force. Okay, so these are some things. These are characteristics that you should know. The composition of the electrodes, which is kind of what we've been comparing this whole time. So the composition meaning we're on reduction potential list. So if they're very far apart, it's going to create a big smaller difference, or you can look at the numbers themselves. The concentrations of the solutions. So we say the standard solutions are 1 molar, and we will use standard solutions every single time we see the not. So that little not right there means standard, which means 1 molar. We will talk about tomorrow, or no, the next day, concentration cells, and they're actually the same cathode and anode identity, but they have different concentrations. So like I'm going to have a 1 molar solution on the anode and a 0.5 molar solution on the cathode, and that's going to create a difference in the electron flow. But we actually will have the concentrations eventually even out because of Le Chatelier's principle, equilibrium occurs. So, but standard is just 1 molar. And then we remember, we just talked about this, all half reactions, reductions. And then you guys tell me qualitatively, or actually quantitatively, the greater the E value, the cell potential, what does that mean about its oxidizing agent strength? So the greater or the lower, the higher or the lower. So what does this mean? What does that mean? Well, no, this is just E. This is E. This is the reduction potential, right? So this one has a high reduction potential. So it's going to mean it's a very good oxidizing agent. And then this last part, I think I've said like 3 times. Yeah.
Like batteries run out because
The cathode gets plated. The cathode gets plated, or the anode runs out, or the the concentrations get to the point where you might have so few ions left on the anode. No, sorry, so few ions left on the cathode in the solution, they can no longer plate. Right. Or rechargeable batteries. Those are ones that have ion flows that can go through a semi-permeable membrane, usually acids. Those are like lithium ion. The nickel cadmium batteries are slightly different. I'll show you a transition of batteries from like then until now. They're very, very complex. And these batteries, these are galvanic batteries, and you can see there's 2 chambers. Most of our batteries now are pretty compact and like single disc. And you know, like in a battery like this is a AAA. There are like 6 discs inside of here that are galvanic cells. Okay, and these galvanic cells put out energy naturally. Each of the discs, though, they can run out at different times. Yeah.
So as long as there's
Right. They won't flow. They have no place to go.
When you use it, it starts floating.
Mm-hmm.
And then when you cut it off,
When you take it out of its circuit, yeah, it has no place to allow the electrons to flow, so they're just chilling. Also, but another way it can be compromised is if there's corrosion or the acid leaks out, and then you don't have a closed system anymore. So there's no salt bridge essentially to replenish the charge buildup. Yeah, that's why battery acid is sulfuric acid. Okay. Looking at this one, this is on your paper. This last one down here. Actually, let me do the next one. This one right here. You guys tell me, based off what you're seeing, and you know I want a galvanic cell, okay? Which of these is cathode, which of these is the anode? Which half reaction goes with which? Do you know that just from the top of your head? So that's a really good thought process. I want some more evidence for this. Okay, so the silver is the cathode because what is its cell potential? 0.799 volts. And what is iron to iron 2 cell potential? 0.771 volts. Okay. Remember, E means cell potential or electromotive. I'm sorry, E means cell potential. E cell means electromotive force. So yes, this is the cathode because it's the higher value. This is the anode. So this is the one reduced, and this is the one oxidized. And you could write up the half reactions. You could draw the cells. The hardest part is figuring out which is which. Okay. So number 9 on the 1 through 9 that you guys did for homework, it said what is the total? What is the N? What is the number of moles of electrons transferred? Can you guys tell me from these half reactions, when you put them together and you balance your electron charge, how many electrons will be transferred? 1 mole, because these actually transfer 1 electron off of each, right? So that you can see the 1 and the 1 mole of electrons here. So whenever you're looking for N later on, we'll actually use N. You're looking for the total moles of electrons released or gained, which is just the coefficient on the electrons in your balanced reactions. Okay, so like the previous one, I think we had 5 and 2, so we had to multiply them by opposites, so we would have had 10 moles of electrons transferred because it was 5 times 2. Remember that example, like the very first cell we drew for today, or our second cell we drew for today. So that's what that is. And I think that's what I'm going to do right now. I'll do this part later. I'll do that tomorrow. And that's tomorrow. Okay. So go grab a Chromebook. Shan's already got hers, guys. You have an hour left. Woo, I'm feeling it.
I'm kind of wondering what kind of battery these are. How much does that kind of?
I don't know. I should look up.
And I was like, you know how you like I wasn't over that. The wrench touched both sides, and the battery blew up.
No, oh my
Like,
God.
I had.
It's shorted out.
I had.
That's insane. I don't know what's inside of a boat battery. I don't know. Like I know like a lawnmower battery. Like a lawnmower or a oh, is it Sam's car? I'm gonna look it up. I wanna find a really good image of all the different batteries from like old times to now. I'll show you guys. Okay, people, go to el website. Okay, look up here, then I'll show you pictures. Good AP Chemistry, Docs, Unit 10. Oh my gosh, we're so close to done, guys. Unit 9, my bad. Unit 9, Electrochemistry. Nuclear, if we can at the end, but I don't know if we'll get to it. We have 3 weeks for exam review right now. So, investigating concentration changes, reactivity, Nernst equation simulations. The one that says simulations. Okay, like that. And you guys will be doing this on paper because I still have your lab notebooks because I'm really trying to get those done tonight. But I have grad school Tuesdays and Wednesdays, and I don't know if that's going to happen. So the first part is you're going to be simulating with some different metals. You're going to be filling the blank. This first part will not take you very long, but just make sure you're following the instructions. So it says to choose a metal and surround it in its own ion solution, so like copper and copper-2 solution and so forth. After you go through the first demonstration, you're going to switch the electrodes, so the anode and cathode are switching places. And so that's what number 11 and 12 down here are indicating. Repeat the changes with the other metal. So that part won't take you very long. Part 2, and there's some fill in the blanks there. You guys can just write down the answer. Complete sentences are not essential for us. The second part has you to complete activities 1, 2, and 3 with lots of metals. I'm going to look through and tell you the one, because you have to write BCs for them. And that's going to be a little tedious. So I'm going to have you guys do a portion of this, but I need to look at it again and tell you specifically which one. So as you're going to do part 1, I'll do part 2 and tell you what's essential. Because you can see it's like complete it for all of these 4 metals and then all these 4 metals and then with HCl. Okay, so I'm going to try to limit this down to about 25% of what that is. Okay? If you can finish part 1 and 2, that'd be awesome. Whatever you don't finish, you can do for homework. Part 3 is something that we will have about 30 minutes in class for tomorrow, but go ahead and look at part 3. Do you see there any questions on there? I see reading, right? Little background, little background, little background. And part 4 is where your questions come in, and it's starting you to try to relate gifts to us, what we're doing now with Electrochem, and then kind of pulling back into some thermo. So I'm trying to get you to us to review thermo now and a little bit more later, because I'm hoping that throughout the whole year I touch on everything 3 times. Okay? Initial review, and then like for real AP Chem exam review. That way you've seen it 3 times and you should be good with it, okay? So part 4 has some questions, and if you get to that now, that'd be great. I'll tell you guys about the thermodynamic review questions at the bottom, but other than that, questions, start part 1, okay? If you want to work together, that's fine, but please stay on task. I know you people, you're social butterflies. What's that? you want to do a lab station, that's fine. If you want to get on a desktop, that's fine. If you want to get two computers and have questions on one and just that's fine.